It's 9 o'clock, so let's get started here. Okay, so we will quickly finish up this graphics section today. Then we're going to start a new section called Principal Component Analysis. Let me remind you that project number 1 is due on Monday, October 14th. Now there was a question, a small question last time regarding in R when you see something like 1L or 2L. So for perhaps maybe, for example, you make an assignment X gets 1L. Well, I guess I had figured that out in the past, and I came across the answer. And basically, what that 1L and 2L means is treat 1 as an integer, treat 2 as an integer versus maybe a real number. Now, the reason why that used to be important is because it would help save in terms of memory. It takes less memory to store an integer on a computer than it does, let's say, a real number that might be, let's say, 1.000000. Okay? And the particular function that we were looking at when we saw this was the Parkour function, and that was written probably about 20 years ago, when memory was more of an issue, we were working with computers. So that's why sometimes in some of these older functions you'll see stuff like this done. Are there any questions before we get going here today? Note that I still can't access my website with Internet Explorer, but I can with I'm using Chrome here. Oddly, when I go to, I've tried it on 3 other computers. One computer works with Internet Explorer. One computer and 2 computers do not work with Internet Explorer. I cannot explain why. It seems like it's more of a computer-based issue versus necessarily a web server issue, and in that case, it's not something I can go to the tech support people here to solve because it's dependent on each computer. So, if this is occurring for you, I am sorry. There's a lot of other browsers out there. Maybe this will give you an opportunity to explore the various different browsers. Okay, so we left off last time about page 49. We were talking about trellis plots. This example deals with the very first trellis plot that I ever constructed that was published. And it dealt with a Monte Carlo simulation study that I needed to summarize, and I didn't want to summarize in the table format that you often see in statistics papers. So I used this trellis plot to help summarize it. In an effort for us to save time here, I'm not going to go over it in class. I would like you to read it. But this is what the trellis plot looks like right there. It really helped us in terms of writing the paper and then getting it published, helped really us form conclusions about which of these statistical methods were working correctly and which were not. If you have questions about this trellis plot, please feel free to ask in our next class. So that takes us then to page 53, where we have some final notes for the graphics section. In particular here, over the last, I would say about 7 years, the biggest trend in writing a book on statistics was to put R in the title, or to be featuring R. And so there's tons and tons and tons of R books out there now, including I'm actually writing a book which has R in its title too. There are a few books dedicated to graphics. In particular, if you like the stuff that we did in this little subsection, I highly recommend the R Graphics book. I have the first edition of this book. I haven't looked too closely at the second edition, but I would assume it's probably better than the first edition. And I have found this book to be extremely useful in figuring out code to construct graphs. Now, also a big trend, maybe over about the last 4 years, maybe 5 years in writing statistics books, has been that you construct a big R package, which of course you don't get compensated for at all. But what you do is you write a corresponding book that shows people how to use the package, which you can get compensated for if people buy it. Now, of course, you're not going to get rich writing a book. Like for example, with my book, myself and my co-author, we share just 15% of the overall price of the book. So let's hope that e-publishing starts taking off even more than what it has now, and that faculty who write books will be e-publishing it. I would have done it myself, but I wanted to see what the experience was like from the publisher, from going the traditional route first before I ever try to e-publish something. But so yeah, so you get 15%. You know, let's say if a book costs $100, so you get $15 off every book. And you know, how many books are you going to actually sell? Well, unless you're writing an introductory statistics book, you're not going to sell that many. So you're not going to get rich off writing a book on a package, but still, I guess it's nice to get a little bit of money. You know, think of it, I guess, for those of us who have 9-month appointments like myself, this is, you could say, a little bit of summer salary. Anyway, so there's 2 books about R packages that focus on graphing. You know, we already talked about the lattice, and we've briefly mentioned the Ggplot2 package. Both of these books are available through our library for free. So those are the corresponding addresses. You can download it chapter by chapter. You know, I've done that myself. Yes? You can. Okay. I wasn't aware of that. That can be a little bit easier, obviously. So this Ggplot2 package, the GG stands for Grammar of Graphics. And this actually, Grammar of Graphics is actually a name of another book that's not necessarily focused on R, but is about graphing itself. That was published, I don't know, maybe about 10 years or so ago. And it gives you a different way to think about how to do graphics without going into all the details. And Hadley Whitcomb came about about 6 years ago. He liked the book, I guess, so he decided to write an R package based upon the same ideas that were presented in the Grammar of Graphics book. And so he called his package Ggplot. Eventually, there was a revision to the package. He decided just to create a whole new package called Ggplot2, and thus then end up publishing a book on it. I had wanted to get to Ggplot2 in this course, but obviously, you know, we've already spent about 3 class periods on graphing itself, and so I just decided, okay, it's just too much. If you want to know more about Ggplot2, take my Tools for Statisticians course next spring. I will spend at least a day on it in our class. The course is going to be listed under, I think, Stat 992. It's a topics course. It might be 892. It hasn't been fully decided yet. But if you're interested, please consider taking the course. But I do recommend it. Talk to me first about the course, because it is primarily meant for PhD stat students. Okay. Now, there are actually some departments of statistics that offer entire courses on graphics. We do not here. At my grad school, K-State, we did, but unfortunately I wasn't able to ever take it. It couldn't fit in my schedule. But here's a nice little website on a graphics course. This is at the Department of Statistics of Iowa. It is offered by a professor by the name of Luke Tierney. He actually happens to be an R core group member. What that means is he's one of 20 people who can actually change the main base R source code. Okay, so he's somebody who's well respected in the area in terms of computing, and that's why he's heavily involved with the development of R. The Department of Statistics at Iowa State, that's probably the largest, you could say, best to Department of Statistics in this area of the country. You know, they have 30 to 40 faculty there, and because of that, they actually have a research group that's focused on statistics. I'm sorry, focused on graphics itself, and those are the 2 professors who are most involved with that. In particular, they have Diane Cook has developed a package called Ggplot2, which is specifically focused on graphing multivariate data. And this is also something I had hoped to get to, and in fact, the software package is actually installed on these computers here. I had it installed, but you just can't do everything. And there is actually an R package that allows you to interface with this separate software package. The interface is called RGGobi. And lastly, there's actually a journal that's published by the American Statistical Association that's at least partially focused on graphics. The Journal of Computational and Graphical Statistics, one of my more favorite journals. They have interesting things there with computing and graphics. Okay, so enough about that. We are done with the graphics section. Are there any questions? Yes?
For a subject matter scientist, control over font size and style is often important in producing graphs. And I have kind of looked through the help on some of these functions you've got, but I'm not seeing.
That's what will be talked about in a whole semester on graphics.
Okay.
So, although it's kind of old, but one of the books on that subject is one by W.S. Cleveland, who's a professor now at Ohio State University in the Department of Statistics. He published a book in the mid to early 1990s on issues like that. You might want to check it out. Okay, so we're going to talk about principal component analysis now. And when I was putting these notes together, I was thinking, what would be a great way to just give you a brief introduction what PCA is. And basically, I don't think I could have done any better than how Dallas Johnson explained it in his 1998 book. So here's a direct quote from Dallas's book. PCA involves a mathematical procedure that transforms a set of correlated variables into a smaller set of uncorrelated variables called principal components. These principal components, or PCs for short, are just simply, linear combinations of your original variables of interest. So what you're doing is you have a multivariate data set. Let's say maybe you have 10 variables. And you're going to and these variables are likely to be correlated in some way. Maybe some pairs of variables are more strongly correlated than others. And what you're going to do is basically find linear combinations of these 10 variables to form these new variables called principal components. The hope is that perhaps instead of having to deal with all 10 variables, and we've seen how that can be kind of difficult at times in terms of plotting to make sense of your data, instead the hope is that maybe just 2, maybe 3 of these new variables, these principal components, are all that you need in order to understand your data set. That is the big picture. So again, what do I mean exactly by linear combination? Just to make sure you understand what I mean. Well, let's consider the serial data. Perhaps, well, in the serial data set, there's 3 main variables, sugar, fat, and soda. Perhaps what I could do is form a new variable called a principal component like this. A simple linear combination. And so what I would do with this equation is for all 40 of my observations, simply apply this equation here so that in the end, I only have y to deal with. So instead of 3 variables, now I have essentially just 1. Okay? That's the kind of things that we're going to be doing. And the goal is that by doing this, that you're not going to lose information. If you lose information, then of course you wouldn't want to do this, because then you're losing stuff to note that stuff that you can learn through looking at your data. So you don't want to lose much information. So then why do we use principal component analysis? Well, for example, it can be used to help detect outliers in your data set. We've looked at some graphical measures that allow us to do this, but still, if you have lots of variables, it could potentially be difficult. So if instead you could, let's say, transform your variables to a smaller set hopefully with these principal components, you don't lose information, but you can transform these variables into a smaller set of other variables and now apply some of the same graphical techniques that we've talked about, but now instead of maybe looking at 10 dimensions, maybe you're looking in 2 or 3 dimensions instead with these new principal components. It can also be, principal component analysis can also be used to help with clustering. What that basically means is that you want to, and we'll actually have a whole subsection on this later in the course, you would like to be able to find observations that are very similar to one another and essentially group them, or what's referred to more as cluster them together. So for example, let's say that we could work with just one principal component, y. And let's say that y ranged from -5 to +5 for some reason. And then let's say if you look at all the particular values in your data set after you form this principal component, and let's say that you have a set of variables, or set of observations that always have a principal component between -5 and -3. And maybe another set that's always between -1 to +1, and another set perhaps is always between 3 and 5. So what we see here is we have 3 distinct groupings of our observations based upon this principal component. That's an idea of what clustering means. Also, you might want to use principal component analysis to help predict classifications. What that means is, for example, with the place kicking data set that we looked at earlier. Every place kick is either a success or a failure. Well, what you could do is find principal components based upon that data, and maybe 2 or 3 principal components would be all that you need to fully understand your data set. And then, similar to what we did here, you could look to see, well, are all my successful place kicks maybe falling here, and all my failure place kicks falling over there? If so, now you have come up with a simple way to predict the classification of the data. And lastly, principal component analysis is sometimes used with regression analysis. If you've had a full course on regression analysis, you've heard of the concept of multicollinearity, and that's bad. If you've not had a course on it, simply multicollinearity means that you have a lot of correlations between your variables, your independent variables that is, and this can cause problems with estimating your slope parameters, like your beta 1, your beta 2, can cause lots and lots of problems. So you want to avoid multicollinearity situations. One way that you often see recommended in some regression books to solve that kind of a problem is to, instead of working with your original independent variables, find principal components instead and put those into your regression models instead of the independent variables. This is not necessarily always recommended by some people, and there's a discussion about that concept in this paper there. We will not go the regression route, but I do want to mention it because sometimes you will see this recommended use. Okay. So then what are the objectives then of principal component analysis? Well, you've kind of gotten a general idea what it is probably already. And the number one objective is to discover that you can see the true dimension of your data. So if you measure, let's say, 10 variables, maybe instead you could actually only work with 2 or 3 linear combinations of those variables, which is easier to work with in the end than 10 variables. To give you an idea of what I mean, here's a plot from the homework in this section. In this plot here, let's blow this up a little bit bigger. Focus on the plot on the left-hand side here. What I did was I simply simulated some data from a bivariate normal distribution. I have x1 on the x-axis. I have x2 on the y-axis. And you can see how the points are somewhat tightly clustered together. But both x1 and x2 are fairly important to look at in that plot, because you see variability in both directions, x1 direction and x2 direction. But perhaps instead of using the regular old XY axis system that we see here in this plot, perhaps instead we could rotate this axis system so that instead maybe I could form a new axis system. Oh, let's call this C1, and this we'll call this C2. I could rotate that so that I have one axis. I have a new axis system, and you can kind of see this displayed over here as well, where I just basically tilted it back to the way that we normally see it. Now, do we need both C1 and C2 to understand this data? No, we only need C1 because all the variability in this data is essentially in C1. Very little is in C2. So if you want, you could throw away C2 and just deal with C1 and basically get the same information out of your data. What C1 is essentially here is what's called the first principal component. This is the kind of stuff that we're going to be doing. This is just represented in the smaller dimensions so that you can see it better. So the true dimension of that particular data is 1, despite there being 2 variables. Now, a second objective, which is not as important, but you hope to be able to achieve it, is that, make sure I am recording, yep, is to try to interpret these new variables, these principal components that you had developed. Now, as I mentioned to you before, basically these principal components are going to be linear combinations of your original variables. So let's just say I form a principal component like this. We'll relate it to the serial data. So y is equal to 0.5 times sugar plus 0 times fat minus 0.5 times sodium. Let's just say that this is the principal component, a new variable. What we can see here, if we want to interpret this principal component, what does it represent in terms of our data? It's simply a contrast between sugar and sodium. That's it. Notice fat doesn't play a role at all. So that's what we're going to be looking at then to try to interpret these new variables, stuff like that. Look to see where you have values that are close to 0 there, and also look at, do I have a positive or do I have a negative value there? Sometimes you can come up with some slick interpretations. More often, though, the interpretations are difficult to comprehend fully. You'll see some examples. Okay. So, let me give you a little bit of a warning in this particular section. That is, it's going to take me a while before I can get to an actual data example. I don't think it comes about until page 17. When I was writing up these notes, I did try to figure out if there was a way that I could give you a data example earlier to help illustrate some of this stuff, but I found it very difficult, and I felt as though I needed to discuss essentially about 12 pages of notes before we can even talk about data. So sorry about that, but I think this is the best way to handle this. Okay. PCA, Principal Component Analysis. You can either do it with the help of the Covariance Matrix or the Correlation Matrix. You're going to see some equivalencies between the two. But in order to do our calculations, to figure out what these coefficients in this linear combination are, we're going to get some stuff from our covariance matrix, or we're going to get some stuff from our correlation matrix. And you'll see why that happens shortly. These principal components that we get, these new variables, are always going to be uncorrelated with one another. So essentially, they are distinct sets of information about your data. Principal component number 1, let's say your first linear combination, is going to tell you something that's unique about your data in comparison to principal component number 2. They're uncorrelated. This first new variable that we find, this first linear combination, this first principal component, it's going to account for as much variability in the data as possible for any other possible linear combination that you could find. Why is that important? Well, in statistics, we often equate information about your data, we equate that with variability. You know, you've seen this in regression settings. You've seen this in ANOVA settings. You want to be able to explain as much information, explain as much variability about your data as possible. Essentially, you want as much information about your data. So think of it in terms of a regression example. You know, you want to find all the independent variables out there that explain what happens to your dependent variable or your response variable. And essentially what you're doing is you're looking at ways that you can explain the variation in your response variable through your independent variable. So variability and information are equated in the statistical science. So this is how the first principal component comes about. Some linear combination that explains as much information, as much variability as possible about your data. Then the second principal component, the second new variable, is going to explain essentially the second most possible amount of variation after you have accounted for that first principal component. And the third principal component can be found in a similar way. You can have up to p different principal components if you have p original variables in your data set. The hope, though, is that you can deal with maybe just 2 or 3 principal components, not p principal components, so that you can essentially reduce the dimension of your data. Okay, so suppose we have a random vector x. It's p by 1, so there's x1, x2, x3 down to xp in it. And I'm not going to specify a particular actual name distribution with it. I'm not going to say it's multivariate normal. Rather, all I'm going to say is that it has some mean and it has some covariance matrix, denoted by mu and sigma respectively. That's all I'm going to say about it. We don't need multivariate normality. You don't need any kind of name distributional assumptions at all in this particular section. Here's what the first principal component looks like. Remember, it's going to be a linear combination of your original variables. This is how you find it. The first thing I'm going to do is I'm going to take x and I'm going to subtract off its corresponding mean. So what's the mean of x minus mu? 0. So essentially you are recentering your data in the end. You want it to have a mean of 0. You're mean adjusting your data. Then I'm going to have this vector A1. The one there corresponds to the fact that this is going to be my first new variable. So A1 is p by 1 in dimension. And it's going to be then, A contains then the coefficients in my linear combination. In other words, applied to the serial data, A1 is going to contain these values. Note that in a small demonstration there, I did not mean adjust sugar, fat, and sodium. It was just a simple demonstration. Perhaps I should have mean adjusted. Okay. So I'm going to take A1 transpose times x minus mu. Or if you write it out, do the matrix multiplication. The first component of A times the first variable mean adjusted. The second component of A times the second variable mean adjusted, all the way down to the pth variable. You add them all up. Okay, so where does this A come from? This A1. Well, this A1 is chosen so that the variance of this linear combination is as big as possible. Remember, variance is equated to information. So if I know Y1, I know as much information as I could out of this data as possible through looking at one linear combination. Well, then, okay, so that's how A is chosen. What ends up happening is this. This variance ends up being lambda 1, which is the largest eigenvalue from your covariance matrix. That's kind of interesting. And then A1 itself is simply the eigenvector corresponding to this largest eigenvalue. Kind of cool that happens. You are not responsible for proof of that. In order to fully understand the proof, you would need to have a full semester of matrix algebra, along with some extra stuff beyond that. For example, when and typically in an applied multivariate course, typically instructors would not prove this. My instructor didn't prove it. Where I first saw the proof, though, was in a linear models course. For those of you who've taken Stat, is it 970 here? Do you talk about this proof? I'm sorry. But that's, for example, where I saw it first. And it requires understanding the concepts of like column spaces and stuff like that. If you do want a proof, this proof is actually in a multivariate book. I think personally that this book is at a higher level than what we would want in our class, although I know this book has been used in the past to teach this. It contains a lot more matrix algebra than what we would do here. Okay. So again, because we are maximizing this variance, we are again essentially trying to get at as much information as possible that one linear combination could find with your data. So what's the second principal component then? So that's the first new variable. Our second new variable is found in a very similar manner. So y2 is going to be our second principal component, our second new variable, and it's going to be a2 prime times x minus mu, where a2 is the eigenvector corresponding to the second largest eigenvalue from sigma. And also you have this additional component that a1 prime times a2 are orthogonal. And we've seen the definition of that in the matrix algebra section. Essentially that means then the product of those two vectors is 0. What this ends up meaning then for us is that the first principal component is going to be independent of the second principal component. And the reason why that's important is that, and this gets at this point here, maybe it's a little bit difficult to fully see this if you haven't had a matrix algebra course. Where is that? There we go. But essentially, orthogonality, or if you're just in two dimensions, perpendicularness, you could say, if that's a word, is basically equated to independence. Okay, and we can see that when I draw this new coordinate, xy coordinate structure here, you can see that those axes are orthogonal to one another. They're perpendicular. This essentially allows you then to work with this, well, the independence part. Now, one of the reasons why I bring this up is that there are other ways to draw xy coordinate systems. So, for example, not true in this case, but you will see in the next section when we talk about something called factor analysis, you could actually do a new xy coordinate system that's not where you don't have a perpendicular or orthogonalness. In some cases, that might be helpful, maybe. You'll see some problems with doing that when we talk about this thing called factor analysis later. I guess that also reminds me. I know I didn't bring this up, unfortunately, earlier, but this comes from the data distributions and correlations section that we did. You might remember me having a very similar discussion about drawing a new coordinate system with respect to when we were looking at the multivariate normal distribution itself. This discussion that we are doing here coincides with that too, so you might want to go back or even review the video on that. Okay, well, what about then the third principle, the fourth principle? They're essentially found the same way. Okay, and you could have up to P, but again, if you're going to use principal component analysis, what you're hoping is that the number of principal components that you use, let's call it D. You hope that D is small. The smaller it is, the easier it is to work with your data. The smaller number of variables you have, the easier it is to work with your data. Okay. I guess I kind of just talked about that on page 6, so I'm going to skip down to the bottom. So, how can we, let's say, numerically measure the amount of information that's available from our data? Well, the measure that we're going to look at, it's not necessarily perfect, but the measure that we're going to look at in terms of principal component analysis is something called total variance. Okay? And here's our covariance matrix. And of course, the variances lie on the diagonal. Again, this is a covariance matrix for our original variables. If you were to add those up, or in other words, in fancy matrix algebra terms, if you take the trace of that matrix, you get what's called the total variance. You're adding up all the variances. So you can kind of think of this as a numerical measure then of the information that's available to you in your data set. And so as you might expect then, our goal is to try to get principal components that explain as much of this total variance as possible. So, from our matrix algebra section, we learned this little nice relationship. That is, the trace of a matrix ends up being the sum of the eigenvalues. You remember the role that the eigenvalues play here. We do a split screen. So lambda 1, oops, let me get back to where I was down here then. So lambda 1 is the variance of the first principal component. Lambda 2 is the variance of the second principal component as well. And so then a measure then of just how much information is being explained by each principal component is simply take a look at this little ratio. Take the lambda from the particular principal component that you're interested in, divide by the sum of the lambdas. So this is the percentage of the total variation explained by, in this case, the j principal component. You want these values to be as high as possible for the excuse me, for the let's say the earlier principal components, like number 1, principal component number 2, and so on. And so then, as a way to decide, well, how many principal components can you use? You could say, for example, I'm going to use as many principal components as it takes to explain maybe 80% of the variation in my data. So you look at principal component number 1, maybe it explains 60% of your of variation. Look at principal component number 2, maybe it explains 25%. Okay, so if you take 2 principal components to represent the rest of your data set, you've explained at least 80% of the variation in your data. That's a high number. Again, variation, equate that with information. So it might just take 2 principal components to explain a lot of the information that's in your data. That's how we choose how many principal components to use. That's one way. Are there any questions so far? Because obviously I've been talking a lot here. Any questions? Okay. So let's talk about determining the number of principal components. Essentially, this is what I just did. Again, the goal is to find the smallest number of these new variables, these principal components, such that most of the data set variability is accounted for. The only way that you can get 100% is if you choose P principal components, if your original data set has P variables. So what you're doing is you're hoping to have a high number, a high percentage. I cannot tell you necessarily what if one overall percentage to always use. I know I use 80% as an example, but of course 90% would be better. 70% might be a little bit worse. Well, it would be a little bit worse. I cannot necessarily tell you, always shoot for 80%, always shoot for 85%. It's dependent upon, obviously, the situation. And even if you do have a lower percentage, it still can be useful to use a principal component analysis. And you'll see examples. So, method number one. What you could say is that I want to account for 100 times gamma percent of the variability in the data, where gamma is some number between 0 and 1. So maybe gamma might be 0.8. So you choose the number of principal components such as at least 80% of the variation, total variation in your data is accounted. That would be one way to go about doing this. Another example is to use what's called a Ggplot. Simply what a Ggplot is this. Plot your eigenvalues, again, those are measures of variability, accounted for by each principal component, versus the numbers 1 through p. And you're going to get a plot that looks something like this. And what you look for in this plot is where does the plot start to level off? We can see that once you get to 3, the plot's leveling off. And it's kind of close to, if I actually were to draw a numerical scale here, close to 0. So because of that, you might say, okay, let's go with 2 principal components. Because anything more is really not helping a whole lot. It's not really explaining that much variation in your data. So those are 2 ways to choose the number of principal components. You can see that there is room here for one person to conclude a set of principal components, another person to conclude a different number of principal components. There is room here. The key is to be able to justify your answer. I've shown you 2 different ways. We'll learn about a third way later. Now, so far, all the calculations I've been showing you, we can't actually do them because we will never know what mu is. We will never know what sigma is in actual application. So how can I actually apply these concepts then to a data set? Well, wherever you see a parameter, you put a hat on top of it. So put a hat on top of mu, put a hat on top of sigma, and now you can do it. So we learned in the data distributions correlation section how to estimate mu, how to estimate sigma. Just simply put that all in there. And in the end, what you get out is, for example, y hat 1 and y hat 2, and so on as your principal components. And let me demonstrate that there. Okay. Excuse me. So of course, just to make sure this is clear, that a hat would be then an eigenvector from your the eigenvector from the estimated covariance matrix. Of course, lambda hat would be then an estimated eigenvalue from your estimated covariance matrix as well. Okay, so possible issues then with using principal component analysis. Notice I don't call them problems, just call them issues. There's 3 of them. First, if the original set of variables are already uncorrelated, well, Pca is not going to help you at all. Where Pca helps is that if you have variables that share a considerable amount of correlation. Why? Well, again, think of it in terms of what we saw here. Essentially, x1 and x2 have high correlation. So if you know what x1 is, you have a good idea what x2 is essentially. And so that's why, this principal component stuff is going to work. If instead x1 and x2 were, if you imagine, let's say, a completely random scattering of points on that particular plot, principal component analysis would not help because x1 and x2 are representing essentially distinct sets of, they're describing distinct parts of your overall problem of interest. Pca does not generally eliminate variables because the PCs are linear combinations of the original variables. So you can't necessarily, let's say, form these principal components and then throw away your original data set. Because you're always finding these linear combinations. So while you can view your data, let's say, in a smaller number of dimensions, you still have your underlying variables in the end. And lastly here, the original variables need to be measured in the same units and have the same variances for PCA to work. Well, obviously, we know, like for example, with the serial data set, sodium is measured essentially in different units than sugar and fat. That means you could have a lot of, and actually we saw that sodium has a lot more variability than sugar and fat. Well, think about how that's going to affect our total variation measure. And we use that total variation measure to account for the total information that's available from our data. So because of that, generally speaking, you should not do principal component analysis on data that is not measured in the same units. Well, how can we get data in the same units? Standardize. So that's a quick fix. So generally speaking, we will always do principal component analysis on standardized data. Now there's actually going to be an equivalence to something else very shortly that you will see too. And I give a demonstration here, and I think you can get a better understanding of it if you read through it on your own, why working with data that essentially has this, working with variables that essentially have the same variance are so important when you're doing principal component analysis, generally speaking. Because that total variation measure can be is so important in doing a principal component analysis. Now, there will be times where you will have data that's measured on the same units. In particular, we will look at a data set coming up. In fact, I think you looked at this in the homework. If you remember the Ggplot data set, everyone should be saying, yeah, I remember doing that in the homework. Yeah. The Ggplot data set actually contains 5 measurements on goblets. And they're all measured, I think, in centimeters. And in that case, it might make sense to not standardize your data and just go with the raw data itself. You'll see that as we go along in this section. Okay. So, a solution to the problem, then, is to use standardized data. An equivalent solution is to use the correlation matrix in the place of the covariance matrix in all of our calculations that we just discussed. Why? Well, remember the correlation matrix is also equivalent to the covariance matrix of standardized data. Let's talk about that some more to make sure you see this. This is actually partially based upon a problem that you had on the test and also in the homework. So let's say I have 2 standardized variables, Z1 and Z2. The covariance of Z1 and Z2 is equivalently equal to the correlation between Z1 and Z2. Why? Because the variances of standardized variables are equal to what? Well, also, one can show, and this was actually discussed in the data distributions and correlation section, that the correlation of the corresponding unstandardized variables is equivalent to the correlation of the standardized variables. So if we think of it in terms of just working with our original variables, unstandardized, in using the correlation matrix, that's essentially then equivalent to using the covariance matrix with standardized variables. Okay? Again, once we get to a data example, I think that will help too. But this is the equivalence here. Okay, so page 13 then. So, principal component analysis is most often applied to the correlation matrix, not the covariance matrix of the original variables that you have. Again, the correlation matrix, P, will generally not be known. So replace P with R, the estimated correlation matrix. The corresponding eigenvalues and eigenvectors of R I will denote by as follows. So lambda, then a hat to say this is from an estimated matrix. Then a star there is to help us differentiate it from using the covariance matrix. So lambda, hat, star is an eigenvalue from our correlation matrix. A hat star is an eigenvector from the correlation matrix. Okay. Well, how do you then determine the number of principal components to use if now you're using the correlation matrix? Well, the first two are exactly the same as what we discussed a few minutes ago. So notice how I have the word variability there. You might be thinking, well, wait a second, now we're dealing with correlations. Well, the reason why I can still get away with talking about variability is because of this relationship that we see there. But when you're working with the correlation matrix, then you have an additional way to determine how many principal components to use. Simply find the number of eigenvalues that are greater than 1. Well, why? Well, remember, if we're thinking of it in the context of using standardized data, the variance of Z1 is 1. The variance of Z2 is 1, and so on. So if you make sure that you always choose principal components that have variances that are greater than 1, and that says that a principal component then accounts for more information than one of your standardized variables. You know, if you looked at a principal component and had a variance, or equivalently the eigenvalue of, let's say, 0.5, then it says that that principal component accounts for 50% of the same amount of variation that one of your original standardized variables would have. Well, why would you use it then? It accounts for less information than an original variable. So this is an easy way then to determine how many principal components to go with. Look at the number of them that have eigenvalues greater than 1. Okay. Let's talk about something called PC scores. As I began with at the very beginning of the, we can go back there. So I mentioned at the beginning here, let me do some erasing as well. Let's say that this is our first principal component. What we need to do now is essentially apply this equation in terms of the serial data to all 40 observations. So observation 1, plug in the sugar, fat, and sodium value, and you get the first principal component value for that particular observation. For observation 2, plug in the corresponding sugar, fat, and sodium value, you get then the first principal component value for that observation. And so by doing that, that's called scoring. And so a principal component's score looks like this in terms of our fancy notation. So why then a hat to say that this is based upon now working with estimated parameters, a star to indicate that we are working with the correlation matrix. The subscript R on Y corresponds to the observation number. R is equal to 1 to n. J there corresponds to which principal component. J could be 1 to P. And simply, you take then that estimated eigenvector from the estimated correlation matrix, multiply it by the standardized values for the rth observation. That's a PC score. If we were not working with the correlation matrix, and we were working with just the covariance matrix of the original X variables, this is how you would find then the PC scores. Essentially, it's the equation that I showed you at the very beginning, except for now we have an extra subscript with an R there. To say which observation we talk. Okay. Now, the elements, these coefficients on our variables are going to be very important to us for the same reason as I discussed before. Sorry to keep on going back in time here. But remember, when I showed you this part on page 3, that we can think of this principal component as essentially a linear combination, essentially a contrast between sugar and sodium, where fat plays no role. So we're going to be very interested in looking at these values. That's going to be corresponding to our A hat star values. We're going to be very interested in those and using those to help interpret then what these principal components represent. And so that's the purpose of what I'm talking about here. So maybe I'm reiterating something that I already kind of mentioned before. But that's what we're going to be looking at. Which of these components of A hat star are close to 0? That says in a particular original variable doesn't play much of a role in our new principal component. Which of these A hat star values are away from 0, either in a positive or negative direction? That tells you, if you have some kind of maybe contrast that a principal component is looking at. I'm going to skip, for now, the rest of the discussion on page 14, 15, and 16 so that we can finally get to a data example. Okay. There are two main functions in R that does the principal component analysis. The main one that I typically see most people use is one called PrinComp, principal components. Another one that I will briefly mention towards the end of this section is called PRComp. They will essentially always give you the same results. It's just the actual computational way that the stuff is found is a little bit different. PrinComp does what I have just shown you so far. Okay, so let's take a look at the serial data again. We're going to focus on sugar, fat, and sodium. Now, in a real application, you probably would not want to do principal component analysis here for two reasons. First of all, you only have 3 variables to begin with. Okay, but this provides us a nice way to begin looking at principal component analysis, so that's why I chose it. Now, a second reason why you would probably not want to use principal component analysis here is what's shown in that it's due to what's shown in the correlation matrix. We've seen this correlation matrix before. What do you think is? Why do you think principal component analysis might not work well here? The correlations between these variables are relatively small. And you're going to see how, when we do these principal component analysis calculations, you will see what happens. And so that's why I think this is also a good illustrative tool, or good data set to begin with. Okay. Now, again, remember sodium is measured on a different numerical scale than sugar and fat, even after we do that adjustment to the data. And so because of that, working with the correlation matrix would be preferred in the situation. Let me jump on over here to tin. going to read in my data, do the nice little serving size adjustment. Okay, let's just go ahead and do that. And here's how I'm using print count. There's a few different ways that you can tell which variables that you're working with. The first way is to use a formula argument. Formula equal, and similar to what we saw with the LM function, you saw like a little tilde that separated the response from the independent variables. Here we use a tilde simply to give, oops, I can't write on there, that's right. Simply to tell okay, I'm using sugar, fat, and sodium, and I use plus signs to separate out the variables. I specify where my data set is. I say I want to use the correlation matrix. And then also I would like my PC scores also calculated as well. Now an alternative way that you could have used this is as follows. X equals serial, and then give the rows, the columns, where the variables are located. This can be helpful when you have a lot of variables and you don't necessarily want to write out or type out every single variable. So this is an alternative. In this case, you wouldn't need the data equals serial argument. And you just go with core equal true, scores equal true. So this is an alternative. Okay. So I'm going to put the results into an object called Pca.save. Could call it something else if I wanted to. I just thought that was a reasonable thing. And then I'm going to print Pca.save to see what happens. Oops. Yep. Thank you. Okay. So what we have here are standard deviations just basically printed out. What are those standard deviations representing? What do you think? So you see something comp.1. Principal component number 1 has a standard deviation of 1.15. So in other words, that first eigenvalue from the correlation matrix is 1.32. So let me actually go over here. So you could say that this is the square root of lambda hat star 1, which equivalently would be then the variance of the first principal component. In other words, the variance of y1 star hat. Oops. With a square root.
In this case, we know that the sum of our eigenvalues should be equal to E.
Very good, yeah. So the sum of the eigenvalues here is equal to 3, because we're working with the correlation matrix. Remember, the correlation matrix is going to have 1s on the diagonal. And so, as a general idea then of how good is this first principal component, I think we said it was 1.32. Is that right? The lambda? So if I take 1.32 divided by 3, we can see that the first principal component accounts for 44% of the total variation in the data. Standardized data. Okay. Now, throughout the rest of the course, You know, we're going to have a number of sections that we're going to be doing, or subsections, if you want to call them that. And each subsection usually focuses on one particular function. So principal component analysis is going to be printcomp. When we do factor analysis, it's going to be a function called factAnal. When we do discriminant analysis, it's going to be a function called LDA and also another function called QDA. When we do nearest neighbor analysis, it's going to be KNN. So each of these subsections are going to be focusing on one particular function, mostly. And whenever you come across a new function, and you're trying to figure out what information is given to you after you run that function in R, there's a number of very common steps that you should always do. The first one is names. We've seen the names function before. Names tells me, well, what exactly is inside this object that was returned from printcomp? Well, I do pca.save, and how do I access part of that? How do I access one of those components? $sign. Okay, let's do, we'll do, which one do I want? We'll do call first. And you can see, well, this is how I actually use the function. This is very useful so that you know how this, essentially all these calculations came about. Let's see, let's do SDEV. Oh, look at that. It's these standard deviations that we had seen. Okay. Let's look at loadings. These are the corresponding eigenvectors from the correlation matrix. Now remember, they're basically these values that you see in each column are essentially then the coefficients in this linear combination. And so why are they called loadings? Well, you can kind of think of these coefficients as being a load on your original variable when you're forming the linear combination. So that's just where that terminology comes from. And we'll see why shortly, why there's nothing printed there. Anyway. And do not pay attention to this part here. This can be misleading. You'll see why too later. Okay. So you should always try names. Use the names function with something. Another thing you should do with anytime you're encountering a new function, you want to know what information is given back to you, use the class function. This was talked in the introduction to R notes. I think it might have been mentioned one or two other times since. Remember, every object in R has what's called a class associated with it. And it just so happens that the class for stuff from printcomp happens to be also called printcomp. Generally speaking, when you write functions, you don't have to have a class return. That's always the same name as the function, but often it's very convenient, so you will see that most often. Now, the reason why it's important to know what that class is remember in R there are things called generic functions and method functions. So if I say method class equal printcomp, methods, oops, I see a listing of what are called method functions that are available to me that I can use with objects that come out of, or objects that result from printcomp. So for example, you see something here called summary.printcomp. If I type summary pca.save, I get this. I get a summary of the information that's inside of pca.save. Now, why was I able to use summary versus summary.printcomp? Does anyone remember? Exactly. Summary in R's terminology, this is covered in the introduction to R notes. Summary in R's terminology is called a generic function because it can be used with a variety of different object classes. What R does when it sees that you're using a generic function, it looks first at what is the class of pca.save. Ah, it's printcomp. And so then it immediately then sends R to a new function called summary.printcomp. So for example, if I were to do this, oops, what did I do wrong here? No, I'm not for sure why that happened. I'll have to think about that. Generally speaking, when you, what's that? Well, just because it's hidden, it shouldn't matter. Unless this is something newer that R is trying to do to prevent people from using this kind of code, which they prefer not to. That's odd. What's that? Do plot dot what?
Just substitute the printcomp as Pca.save.
Well, yeah, I could do plot Pca.save. I could do that, yes. But I should be able to access the method function directly. So I know it does actually exist. I think this was briefly mentioned in the introduction to R notes. If I use the function getAnywhere, this helps me find the actual function, and there you see it. It does exist, but for some reason R is not allowing me to access it directly. I don't know why. Maybe I shouldn't try to do stuff that I had not tried before class. Anyway, I'll look into that. If I can figure out an answer, I will let you know. Because we looked at some examples actually in the introduction to R notes where there was no problem using one of these method functions directly. Okay. It's not a big deal anyway. I was just trying to show you some of the inner workings of R, which fortunately didn't work very well. So anyway, with this particular summary function then, the way that it's typically used is with some additional arguments. So I'm going to say summary Pca.save like what we saw before. And then say loadings equal true. What this tells R to do is actually print those eigenvectors, the coefficients on these linear combinations. And I'm going to say cutoff equal to 0 as well. You'll see why I did that shortly. Okay. So we see some information that we had already actually saw before. We see these square roots of the lambdas, the standard deviations of each principal component. We also see the proportion of variance explained by a particular principal component. So if I were to take 1.15 divided by 3, or in other words 1.15 divided by the sum of these eigenvalues, I get 0.44. The second principal component, 0.312. The third, 0.246. Remember, each principal component, as you successfully go down in terms of number, or I guess actually go up in number, will explain less and less and less of the variation of the data. Then these loadings, these are the eigenvectors from the correlation matrix. Just to illustrate that, I can use a function that we've seen before called Eigen with the correlation function. And you can see that here's the first eigenvector, and it matches. 1.32 for the eigenvalue is the square of 1.15. So to some respect, do we really need printcomp? Well, you can easily use Eigen to do your calculations. And then you have to, as you will see next time, you would have to find the scores yourself versus them automatically calculated. Lastly, this cutoff equals 0. What this does is it makes sure that the absolute value of all these eigenvector components, the absolute value of those eigenvector components will be printed as long as, I'm running out of time and I'm not making sense. Let me start again. Essentially, if the absolute value of any of these components is greater than 0, it will print it. Obviously, that means all of them are going to be printed. Now let's look at the default. When I don't run that, you see what happens. You don't see that one printed now. If you remember, that was 0.09. The default is using a cutoff of 0.1. Why does R do that? Well, when you have values in your eigenvector that are close to 0, that says that particular variable, corresponding variable, does not contribute much to the principal components. So that's why it will automatically chop it off and not even print it at all. I like to see it and make the judgment myself, so that's why I will always say cutoff equal to 0 there, so that they're always printed. Okay, we are out of time, unfortunately. Are there any questions? Okay, that's it for tonight.